Okay, folks, last lecture of the semester. If you can believe it, I cannot. It has gone by way too fast, and we're going to end this semester out talking about lasers. So this will just be a brief lecture, and of course we'll get into more info during our live lecture. Okay, so the first place to start is, what does laser stand for? So it is an acronym. Light amplification by stimulated emission of radiation. So there's a couple requisite things we have to make a laser. For one, we have to have a cavity capable of undergoing resonant modes. So in our cavity, so I'll just kind of put two elliptical mirrors around here. We, of course, have some molecules in there. Those will be our lasing molecules. And normally in room temperature, these are at thermal equilibrium, right? Where the majority of molecules will be in their ground state. And occasionally we might see one in an excited state. In this resonant cavity, we pump them up using some type of excitation source. So this could be another source of light, or it could be an electric discharge. Either way, we pump them up and get this population inversion. So you can see we've had a lot of our lasing molecules go up into this excited state. We continue making this excited state by continuously pumping them up to maintain this population inversion. And as these molecules then crash back down to their ground state in this resonating cavity, if we've designed the cavity correctly, the length will be some resonant mode, some 1/2 integer of the wavelength that we're trying to amplify, right? That's what this step is all about. And we can amplify that signal in this resonant cavity. So the way in which we create a population inversion is based on not only our pumping source, but also what we're using to make our laser action. So this is not just a simple go up to one state and then crash back down. We need to have multiple states to create this population inversion. So our pump is fast. So this process goes from the ground state to some intermediate state very quickly. We will now have some lag, whether it's radiative or non-radiative. Typically it will be non-radiative, where this goes down to our laser action state. And because of this lag, we're able to put more molecules in this upper state. So we can put them up faster than what they can crash back down in. So there's a kinetic competition there. And then finally, we get this laser action in our resonant mode from designing it to have a requisite length. We could also have a 4-state system given by this picture, where we have this fast pumping band, and then we get this lag going from the intermediate to the lasing action. And then eventually, of course, we'll have another delay to get down to the ground state. But overall, this will also help us create this population inversion, where the majority of our molecules are in this upper lying state, which is how we get this really intense beam of light. So there are two main modes of laser operation. One is called CW, or continuous wave, where the cavities are operated continuously without overheating. And because they need to operate without overheating, they typically have really low power, so like into the milliwatts and lower. On the other hand, we can have a pulsed laser, where the lasing action is pulsed to relieve excess heat that might build up and give more power at each laser pulse. So for example, here is a picture showing our cavity, and this switch might be located in the length such that it makes it non-resonant. And now when we allow that switch to move or shift around in some way, this will give us a resonant mode, which allows us to get a pulse. So we often refer to that as Q switching, where we're switching this thing off and on and off and on and getting these very high intensity laser pulses. And so as an example, in a pulsed laser, we might see like a nanosecond time delay between pulses, followed by like something really short, like a 1 picosecond duration. So like if I could zoom in on this peak, right, we would see some kind of width to it where the full width at half max will be maybe on the order of picoseconds, or for some of the very fastest lasers on the order of about 100 attoseconds. So these can be very, very fast depending on the construction of the laser and the cavity mode. So I just want to describe a few common types of lasers. Probably the most common you'll ever encounter is the Heaney, right? This is the standard garden variety red laser pointer, right? So that we all know and love. So these things have a ratio of about 5:1 helium to neon. And they are pumped up through this electron impact. So you have to have power in one of these things, typically a battery for very weak lasers, or you could even have a very high-powered Heaney laser that would require an external power supply, something more than just like a battery. So we get this electron impact that pumps up our helium. Helium is our excitation source. And so now we can get up all the way to this singlet S state here. And through collisions with neon, this will also pump neon up because its levels are at a very similar energy, as you can see there. And following that, we could, and this collision is actually what gives us our lag. You might be saying, well, why not just pump up the neon? Well, that wouldn't create a population inversion. We're getting a population inversion from this quick pump and then this slower conversion over to the neon energy source. So this allows us to pump a lot of molecules into their excited state, or in this case, atoms, helium atoms. And now you can see for most Heaney lasers, the resonant mode is given from this 5s to 3p transition, which gives you 632, that beautiful red color. But some of the more sophisticated Heaney lasers can give you a green line or a yellow line or an orange line. So for example, if you make a resonant mode a little bit longer, you can get down to that green line, or you could even get down to that orange line, and that's purely based on the construction of the Heaney. Again, most of these are designed to give you that resonant mode for the red line. So there's another common type of gas phase laser that I'll describe, which is the CO2 laser. So these are some of the most powerful lasers in existence. And as such, CO2 lasers are typically used for laser drilling, as you can see right here. So there is enough power in this laser that it can punch a hole through materials. So the CO2 laser is typically made up of mostly helium as background gas, and nitrogen, which is our pumping source, and of course CO2, which is our lasing material. And now similarly, a power supply will pump up into its various excited states. And now we get a lag as that energy transfers over to carbon dioxide. And these lasers will actually come from the infrared line at 10.6 micron due to the anti-symmetric stretch relaxing down to the symmetric stretch. So that laser line, right, it seems like, oh, maybe that's not going to be very powerful because it's infrared. But it has nothing to do with the wavelength and everything to do with the intensity. So these give you really, really high intensity laser lines, enough so that you can punch a hole through materials, which is kind of cool. So another type of common laser, which is a little bit older but still used commonly, are dye lasers. And these take advantage of fluorescence. So typically you'll have some type of fluorescent dye that is flowing into some, cuvette. You can see I've got a picture of one right here. So you can see these tubes right here. These are the fluorescent dyes. And so they are fluoresced by this pumping radiation. And you can see that would be this white light here that's making it fluoresce. And now you create a cavity about that fluorescence. And you can kind of see that pictured in there. There's our cavity. And now based on what you're getting and the size of the cavity, you'll get a certain wavelength out of there, which typically has to be fine-tuned if you want a very precise or narrow laser output. So if you recall, like from the intensity of a fluorescent spectra, it might be some complicated looking thing representative of the vibronic structure of the molecule. So this tuner or this monochronometer will select one narrow wavelength of that band that comes out. And typically the band that comes out of the cavity will be somewhat narrow. It has to be, right? That's how it's amplified in the cavity. But the monochronometer here, or the tuner, will give us an even finer wavelength so that we can get, a proper laser, which is typically one single wavelength. So, and then the final type of laser I'll describe, which is the most common solid state laser, is the YAG laser. And so YAG stands for yttrium aluminum garnet. So the laser material is this neodymium YAG crystal. So that whole entire cavity is this crystal. And you can see there, it's the neodymium that's responsible for the lasing. So that neodymium-3, here's the energy surface of that. And so similarly, you'll use these lamps to pump the neodymium up into its pump band. And then we get non-radiative transfer to this upper level. So that creates our delay or our lag. So we get a population inversion. And then the neodymium neodymium laser action will also give you a very strong IR line. So that 1064 nanometer is in the IR, and you usually get a very intense line from the YAG. And oftentimes this can be constructed in a way, or it can be coupled with another device that will give us harmonics of this line. So typically the first harmonic of the YAG is used more commonly than the principal. And if you think about this quick math, the first harmonic of a YAG is 532, right? Half of that wavelength, which puts us in the green. So the YAG laser is commonly used in the Raman spectroscopy technique, right? If you guys recall, 532 is the most common excitation source used in the Raman technique. And it comes from the first harmonic generation of this strong 1064 YAG line. Okay, so there's all kinds of other lasers that we could describe here, and we'll talk more about this in the live lecture, but I just wanted to give a general overview of lasers and some of the more common types we'll see. So that's it, folks. It's been a great semester. I hope you enjoyed these videos. If you've made it all the way to the end here, congratulations. Thanks very much for staying tuned in. I wish you nothing but the best of you. I hope you are successful in all of your future